consequences of theory of relativity is time dilation. So what do we mean by time dilation? We are going to look at it, or you are going to understand it better once we derive an equation for the time. So you are seeing here two illustrations. One is if the observer is at rest. If for example meron tayong clock, okay, for example meron tayong pulse of light here, tapos meron tayong clock. Pagkadaan ng light and then pag bounce back niya, so marirecord yung time. Ayan yung tinatawag nating light pulse clock. Okay? So again, punta dito yung light and then it will bounce back. So that is the proper time. If the observer is at rest, and also this one, our light pulse clock, is also at rest. But what if ang light pulse clock naman natin ay nasa spacecraft, which is already moving with a certain velocity? Okay, what will be the time recorded by the observer on Earth compared to the time recorded by the observer at the spacecraft? Okay, so yun yung time dilation. So let's take a look at the first one. Okay, let's recall or let's relate it to kinematics. For kinematics, we have velocity equals distance over time. So here, let's assign the distance, this one, that will travel by the light, or that will be covered by the light as L0. And then the time here needed would be the proper time T0, and then C is naman the velocity of the light. Okay, you can see here that the light will travel from point 1 to 2, and then it will bounce back. It will travel from point 2 to 3. So it will cover dalawang distance na at a particular time interval T0. Okay? So we have here, we can consider the distance as 2L0. So we have the velocity of the light, 2L0, divided by the time, or the T0, or the proper time. So let's assign velocity for light kasi siya. So we have C as the speed of light, 2L0, divided by our proper time, T0. Okay? So that's our first equation. We have C, or the speed of light, is equivalent to 2L0 over T0. If we wanted to derive an equation for T0, or the proper time, we have T there. So cross-multiply lang tayo. We now have 2L0 over C. Okay? So yun yung if the light pulse clock is at rest relative to the observer, we have the proper time as twice the length divided by C. So take note of this equation. Okay, so take note for this equation, we have the proper time equals 2L0 divided by C, wherein C is the speed of light, and then the L0 is the distance that the light has to travel. Okay, now let's take a look at what if the light pulse clock is at a spacecraft. Okay. So you have here, it's as if the motion of the light pulse is no longer straight but in a zigzag, or in a zigzag pattern. So the light will travel on this path, and then it will bounce back traveling this path. Dahil nag-move na yung spacecraft natin. Yeah. If we are going to describe the spacecraft, if we are going to describe the motion of the spacecraft, we have here, let's say at this point, up to this point, it has already traveled a particular distance. And then recall also, in kinematics, we have velocity equals distance over time. So that distance traveled is equal to Vt. So, yan. The distance from this point to that point is VT. Okay? But later, we are going to analyze, we are going to use this part. So, half niyan, okay, half of that is VT divided by 2. Okay? Now, what about this one? This one is, they will also travel twice pa rin nung distance. So, at a certain time interval, T. So, that means, if ito lang yung titignan natin, the time therefore is divided by 2. So, distance dito, at this point, let's take a look at this point. If we are going to look at this point naman, up to this one, okay, let's say it will still travel a distance D, pero dalawa siya, it has to travel twice distance. V equals distance over time, pero yun nga, it has to travel twice the distance divided by time. Pag dalawang ganyan. But, kung half lang, still the speed of light is c. There, distance is equal to, the distance is equal to vt, so the speed of light is c. However, the time needed is only half. Kasi nga, ito lang siya. Okay? Alright, so that is consistent. Now we have here, let's label this one as, CT divided by 2. And then for this, same lang naman yung distance niya dun sa when it's at rest, so we can stick with L0 pa rin here. Okay? So there. Let's continue solving this. Okay, so if you're going to draw, a right triangle here. Okay, so we have here, if we are going to have here the right triangle, so let's let's write down the variable. So half kanina, this is half, that's VT over 2. And then for this one naman, it's CT over 2. And then for this is the same as L0. Okay? So now we can express the relationship of these three using Pythagorean theorem. Wherein we have, recall that Pythagorean theorem, we have c squared is equal to a squared plus b squared. So this is our longest side. We have CT over 2 squared equals, ang a natin, we can have this one, VT over 2 squared plus L0 squared. Okay, let's evaluate that equation further. So let's square everything here. We now have c squared t squared over 4 equals v squared t squared over 4 plus L0 squared. Okay, now what we want to have here is an expression for time. So let's combine terms with t. So I will transfer this part. Okay, itong equation na to, I'll transfer it on the other side. So I will subtract v squared t squared over 4 here. And also on the other side, we now have, palitan natin ng color.
Let's do this.
Okay, so let's derive it further. I will combine terms with t. So we have here c squared t squared divided by 4 minus v squared t squared divided by 4 is equal to L naught squared. Okay? So here, as you can see, we can factor out t squared. Pati yung 4, we can already factor out. And then what we have would be c squared minus b squared. So let's continue solving this one. Now factor out t squared divided by 4. Then we have c squared minus b squared is equal to L naught squared. Again, our aim is to get an expression for time. So let's just continue solving this. T squared is equal to, and let's divide everything by, okay, let's multiply everything by 4 and then divide it by c squared minus b squared. So we now have here t squared is equal to 4 L naught squared divided by c squared minus b squared. And looking at this, we can also extract c squared from the equation. Or we can also factor out c squared. From the equation, we have t squared is equal to 4 L naught squared divided by c squared. Since na-factor out natin siya, this will become 1. So that when you distribute, you will have c squared minus v squared over c squared. Para when you distribute also, it will still become v squared. Okay? So after that, let's take the square root. Okay, we now have, taking the square root of both sides, okay, we'll now have t squared, or t, is equal to 2 L naught divided by c, then square root of 1 minus v squared over c squared. So I think this equation looks familiar already. Okay? Okay, again, that is our derived equation. We have the t equals 2L naught divided by c times square root of 1 minus quantity 1 minus v squared over c squared. Now recall, in the first equations that we had, when it's at rest, okay, when the observer is at rest relative to the light pulse clock, we also have an equation wherein proper time t naught equals 2 L naught divided by c. Okay? Okay, so looking at our equation, we have 2 L naught divided by c is also the same as, 2 L naught divided by c is equal to the proper time. So we can now have an equation relating this time t and then the proper time t naught. So t now is equivalent to t naught divided by square root of 1 minus v squared over c squared. Okay, so we now have here the final equation wherein we have t equals t naught divided by square root of quantity 1 minus v squared over c squared, where t naught is the time interval on clock at rest relative to an observer, so that is also known as proper time, and then t is the time interval on clock in motion relative to an observer, v is the speed of relative motion, and then c is the speed of light. Okay? Now, if time is relative, the length should also be relative because as we have mentioned, when we talk about the speed of light, it is constant. Now, let's take a look at this system. Though the speed of the spacecraft is constant based on the observer on Earth and also based on the observer inside the spacecraft, so the velocity are the same. Since time will be different, therefore we are expecting that the distance should also be different. At faster speeds, objects and distances appear shorter. So that is length contraction. So you have here, on the illustration above, okay, you have here the observer is on Earth. So the observer on Earth will see the length, distance from we'll see the distance between two planets to be L naught, or that is the proper length. But for a moving observer inside a spacecraft, the length that he or she will observe will be L, and is affected by the relative velocity. So what will happen, or how do you compare L naught and L? So that will be length contraction. And then let's go and let's derive the equation. Okay, so the next part would be about length contraction. If time dilation, the time changes also with respect to the observer. Yung observer sa Earth will measure different time dun sa observer natin sa spacecraft. When we say proper time, and then the spacecraft is moving, the proper time is the one measured by the observer inside the spacecraft. Tapos yung delta t naman, that is the time measured by the observer on Earth. So, explain din natin siyang mabuti dito sa length contraction. What is L naught, what is L, tapos ano yung delta t naught at saka delta t. Now, if you are going to look at this, okay, if we are going to look at this illustration, so we have here, delta t is the time measured on Earth or on the observer on Earth. And then, yan yung proper length na alam niyang distance. If you are on the observer, or if you are the observer on Earth, kung ikaw yung sa Earth, yan yung tinatawag nating proper length, which is the actual distance from the Earth to the Alpha Centauri. Now, kaya L naught because that's the proper length, okay? Pero yung time natin na proper time, medyo baka ma-confuse kayo in using the naught tsaka yung walang naught. Yung proper time naman natin, yan yung time measured by somebody who is inside the spacecraft. So, yan yung nare-record niyang time. Pero this one, the spacecraft is moving at the velocity v. So, yung length na mame-measure niya is the length L. Okay? So, there, since nagmo-move siya, we are going to expect yung length na mame-measure niya ay different from the length measured by the observer on Earth. So, yan yung ide-derive natin. Basta do not be confused with the proper time, ano yung proper time, ano yung proper length. Okay? So, ito naman, halimbawa, iniisip niya, since we have motion is relative, according to the observer, siya yung at rest. Pero itong mga to, like the Earth and then the Alpha Centauri, it's like they are moving this way to the left, according to the observer here. Okay, so ganun yon. But according to the observer on Earth, ito namang spacecraft na to, it's moving to the right. But their relative velocities are the same. So, pareho sila ng velocity. Now, let's derive the equation here. For the velocity here, again, the velocity is distance over time. So, dito, according to the observer on Earth, ang alam niyang distance na tinravel ng spacecraft is the L naught, which is the proper length from the Earth to the Alpha Centauri. Pero may measure niyang delta t is yung delta t na walang naught. Okay, so that is clear. This velocity is the same also as the relative velocity na ma-observe ng astronaut inside the spacecraft. So we also have the same v. But this time, yung na-observe niya is the length. Or this is the distance that the astronaut observes. So we have L. Pero ang gagamitin niyang time is yung time niya inside the spacecraft, which is the proper time, delta t naught. Okay, do not be confused with that. So, yan yun yung mame-measure ni astronaut. Okay? Ito naman, yan ang mame-measure ng observer. Okay, these equations, yan na may ma-observe ng observer on Earth. Okay? So, let's move on to the derivation. Take note also that they are the same. Okay, let's continue. We have here the velocity measured ng observer sa Earth ay equal to sa velocity measured ng observer sa spacecraft. Okay? So, sa Earth nga, we have the proper length L0, then divided by yung time measured by the observer on Earth, yan yung delta T. Okay, that is not the proper time dun sa spacecraft. For the velocity naman, according to the astronaut dun sa spacecraft, we have yung mame-measure niya is L. Divided by yung time na dala niya dun sa spacecraft, yun yung delta T0 ang mare-register. Okay? So, they are equal. So, let's derive an equation for L. So, ang L natin, since we are looking for this, let's multiply everything by delta T0. Okay? So, our L now becomes L0 delta T0 divided by delta T. So, this is our equation for the length na na-measure na astronaut. Okay, but let us recall, pwede natin magamit yung equation natin for the time dilation. Wherein in time dilation, we have an equation na, so we have here, time, or the proper time is equal to T squared of 1 minus V squared over C squared. So, pwede natin gamitin yan. If we are talking about time interval, gawin lang natin delta T0 is equal to delta T square root of 1 minus V squared over C squared. So, you can see here, you can see now in the equation, meron tayong delta T0 divided by delta T. So, yan. So, here we can divide the equation by delta T. Okay? So that we can cancel this out. And then, meron na tayong delta T0. Sige, let's have it step by step. Delta T0. Okay, we now have delta T0 divided by delta T is equivalent to square root of 1 minus V squared over C squared. Okay? So, we can now substitute this equation, ang delta T over delta T0 over delta T, pwede na siya nating i-substitute here. Okay? So, for our equation, ang final equation natin for our final equation, therefore, for the length, okay, let's use another color. So, let's take a look at the final equation. We now have L is equal to L0 and then the square root of 1 minus V squared over C squared. So, ang C natin, this one is always approaching the speed of light. So, itong expression na to is always less than 1. So, kung ito ay less than 1 multiplied by the proper length, that means the length, this length, measured by the astronaut is always lower than or shorter than the proper length. Okay, so that's our interpretation for the length contraction. And then also, ang masyo-shorten lang is the dimension also ng velocity niya. Halimbawa, going back to our illustration. Okay. Now, let's go back to our illustration. So, you can see here that the velocity of the spacecraft is horizontal. So, yan lang yung dimension na masyo-shorten. So, the dimension na masyashortan ay only at the x-axis, if we have here, yung x-axis natin. So, titignan nyo that the length measured here, dito, ay shorter than the proper length. Pero yung halimbawa, meron siyang dimension na height, the height will be the same. Ang mababago lang yung horizontal. Okay? So, that's the meaning of length contraction. So, here is our final equation. For the length contraction, we have L equals L naught square root of 1 minus V squared over C squared, where L naught is the proper length. Okay, again, from the situation that we had, yan yung length measured by the observer on the Earth. And then V, or L, is the length measured by a moving observer. It is measured by, let's say, for the astronaut inside the spacecraft. And then V is the speed of relative motion. And then C is the speed of light. Okay, so next is to solve sample problems on time dilation and length contraction. The first one, what will be the mean lifetime of a muon as measured in the laboratory if it's traveling at a velocity of 0.6 c, or is also equivalent to 1.8 times 10 to positive 8 meters per second with respect to the laboratory? Its mean lifetime, or its mean life at rest, is 2.2 times 10 to the negative 6 seconds. So what? Okay, mu1 is traveling at 0.6 c. So yung proper time niya, or the proper mean life at rest, is the 2.2 times 10 to the negative 6. So yan yung delta t naught. We are looking for delta t. So you have here delta t is equal to the delta t naught, which is the 2.2 times 10 to negative 6 seconds divided by the square root of 1 minus, ang velocity natin ay 0.6 c. So that is 0.6 c divided by c. Then you have to square it. Okay? So that makakancel na natin ang c square. So our answer here, let's solve. Okay, we have an answer of 2.75 times 10 to negative 6. Okay, 2.75 times 10 to negative 6 seconds. So, it's as if parang mas na humahaba pa yung time niya. So, as you can see here, as measured by the laboratory, it's 2.75 times 10 to negative 6. If it's moving at a speed of 0.6 c. So, yun. When it's associated with the velocity approaching the speed of light, mas humahaba yung kanilang mean life. Okay? So, that's the meaning of our answer. Next item. Okay, so next item. A spacecraft is moving relative to the Earth. An observer on the Earth finds that between 1 p.m. to 2 p.m., according to her clock, 3,601 seconds elapsed on the spacecraft's clock. What is the spacecraft's speed relative to the Earth? So here, you have to identify kung ano yung proper time at saka yung delta t. So in this case, our delta t naught, which is the time dun sa spacecraft, that is 1 to 2 p.m. So that is 3,600 seconds. Pero dun sa na-observe naman ng observer sa Earth, it is 3,601 seconds. Okay? Kasi nga, the concept of time dilation, yung proper time will be shorter than, yung proper time, the time recorded in the moving spacecraft, will be shorter than the time na recorded nung observer at rest. Okay? So, let's derive an equation for V. Okay, you have here delta t is equal to delta t naught divided by square root of 1 minus v squared over c squared. Now we are looking for v, that's why we have to square both sides. So we now have delta t squared is equal to delta t naught squared. Then matatanggal na yung square root sign natin. We have 1 minus v squared over c squared. Okay, deriving it further, we can now cross-multiply this expression to this. So we have 1 minus v squared over c squared is equal to delta t naught squared divided by delta t squared. So let's continue solving this. I am only after velocity, so I can transfer this expression on the other side, tapos ito naman sa kabila. So we have to change the signs. We now have 1 minus, so we now have here 1 minus delta t naught squared over delta t squared is equivalent to v squared over c squared. Pero we are only looking for velocity, so we can multiply everything by c squared. So we now have 1 minus delta t naught squared over delta t squared, then multiplied by c squared, v squared. But we have to get the square root of both sides, kaya cancel na yan, and then square root of this. Our final equation for velocity is the square root of 1 minus delta t naught squared divided by delta t squared. So let us substitute the given. Okay, we have here square root of 1 minus, ang proper time natin again is the 3,600 seconds. So 3,600 divided by 3,601 seconds. Squared, squared. And multiplied by, let's just use 3 times 10 to the 8 squared. That will give us the velocity. So our answer would be so for our velocity, we now have 7,069,595 meters per second, or we can also express it as 7.07 times 10 to positive 6 meters per second. Okay, so that is the velocity of the mu1. Alright, so our answer is 7.07 times 10 to positive 6 meters per second. So that is the relative velocity of the spacecraft. Okay, so let's solve this. Mavis boards a spaceship and then zips past Stanley on Earth at a relative speed of 0.6 c. At the instant she passes, both start timers. At the instant when Stanley measures that Mavis, si Stanley is on Earth, he measured that Mavis has traveled a distance of 9.00 times 10 meters times 10 to the 7th meters past him. What does Mavis timer read? Si Mavis naman yung nasa spaceship. So, solve muna natin yung timer reading ni Stanley on Earth. So, we have here the velocity. So, we have here the velocity equals yung proper length niya divided by delta t. Wherein ang delta t natin here is measured by Stanley. So we are looking for delta t. Delta t is equivalent to the L naught, which is 9 times 10 to the 7th meters, divided by yung kanyang velocity, which is 0.6, times c is 3 times 10 to the 8. So, ano yung delta t? Okay, the delta t that we have here is 0.5 seconds. Okay, this one, okay, ang delta t natin ay 0.5 seconds. Okay, this one is the time measured by the Stanley. Pero ang tanong, what does Mavis timer read? So, ang kay Mavis, yung delta t naught. Wherein we have an equation, okay, delta t naught is equal to square root of 1 minus v squared over c squared times the delta t. Okay? So, let's substitute here. Ang delta t naught na natin is equal to the square root of 1 minus, ano yung velocity natin? That's 0.6c c squared divided by c squared multiplied yung time na na-measure ni Stanley, which is 0.5 seconds. Okay, so the delta t naught is equal to, let's check, okay, the answer here is 0.4 seconds. Okay, so at the instant when Mavis reads 0.5 seconds on her timer, what does Stanley read on his? So ito, since ito daw, na-read niya ay 0.4 seconds sa timer niya, at the spaceship, therefore naman yung reading ni Stanley is 0.5 seconds. Okay? Okay, so one problem in length contraction is this. A rectangular painting measures 1.0 meter long, ay tall, and 1.50 meter wide. It is hung on the side of a wall of a spaceship which is moving past the Earth at a speed of 0.9 c. What are the dimensions of the picture according to the captain of the spaceship? And then what are the dimensions as seen by the observer on Earth? So here, since kasama naman niya ngayon yung painting inside the spacecraft, so the dimensions given, yan yung proper length. Wherein the observer is inside the spacecraft, the same with the painting. We are only going to look for one dimension since it's moving horizontally. So, titignan lang natin yung width, 1.5. According to the observer or the captain in the spaceship, it is still 1.5 meters. So, that's our proper length, L naught. Now, we are looking for what are the dimensions as seen naman by the observer on Earth. Okay? So, we have here, L is equal to L naught. So, that's the proper length, yung ating 1.5 meters multiplied by square root of 1 minus, it's moving at a velocity of 0.9 c. So, 0.9 c, then you square it, divided by c squared. So, ganyan lang yung ating solution. So, our answer now will become okay, our answer for the length is equivalent to 0.65 meters. So according to the observer on Earth, umiksi yung painting, which is moving. Okay? Pero of course, according to the captain, since kasama niya yung painting, the painting still measures 1 by 1.5. Okay? So do not be confused with the concept. Depende dun sa kung sino yung nag-observe at rest, relative dun sa length na mina-measure. Okay? So I hope you understand the concepts of time dilation and length contraction. Then after this lesson, we will also have relativistic momentum. Hi everyone! So today we are going to talk about twin paradox. What if you have a twin sister and then you're going to stay on Earth and then she will be sent outer space? Yeah, she will be riding on a spaceship or on a spacecraft. So what will happen to the observation of time? Okay, so based on your observation, the light in the spacecraft has to travel a longer distance. Since we have mentioned that speed of light is the same, so dapat yung time then will be different since the length that they have traveled seems to be different. So let's now talk about twin paradox. So it seems that your twin sister on the spacecraft will have a slower time compared to your time. So yung time mo takes faster than the time on the spacecraft. And then we are expecting that the one on the spacecraft will be younger than you. Pero since it's a paradox, that means para dun sa tao sa spacecraft, you're also younger. But what happens here is different. So who is now telling the truth? The one in the spacecraft is actually accelerating when she comes back. So it's no longer an inertial frame of reference. It's already an accelerating reference frame. So that is covered by general relativity. So the truth is, she will still be younger than you. Okay, since the spacecraft now is accelerating towards you, so that means for the spacecraft or for the one on the spacecraft, the time is shorter. So you're expecting that you will really be older than the one who was sent in the outer space. So if you want to be younger, then you should be sent to the outer space.